Swayam Prabha. Digital India. Educated India.
So, welcome back everyone, and in this module we will talk about linear oscillations and its normal mode expansions. Okay, so let us start our discussion. Linear oscillations and normal mode expansions. Okay. So, when we talk about linear oscillations, typically we will talk about oscillations which are small oscillations of the particle, right? So, the key concepts we are trying to cover, the key concepts in this module we are trying to cover is undamped to begin with, undamped and damped oscillations, driven and coupled oscillations, and so on, right? So, we see that the linear theory gives good approximations, and for small oscillations we are going to solve the problem explicitly. We will give analytical solutions in our case studies. So, we have, for example, now we have the body on a spring, okay. So, we have this is the first case we will study. So, we have a mass which is connected to a spring, and this spring is trying to drive this object of mass small m, and typically this mass m is going to show some linear oscillations which is along the horizontal directions, okay, and we want to study the motion of the system. So, body of mass m, connected with light spring. Okay, so to begin with, the spring itself will act as a restoring force on the particle. So, the spring will show a restoring force. Okay. So, if the particle is stretched along the right, the spring is going to show a restoring force along the opposite direction, that is left, and so on and so forth. So, the restoring force will be, let us say that this is a linear law. Let us say this is minus alpha times x, right, where alpha is my spring constant. And here in this description I have used the so called Hooke's law, that is the linear law for springs. In our later discussions, when we talk about more complicated springs, we will try to show with more generalized Hooke's law scenario. Well, may not be in this module, but later modules. And then let us also further add the fact that we have some sort of a frictional resistance acting on the particle. So, again, this frictional resistance will be acting opposite to the motion of the particle, and this is going to be proportional to the velocity of the particle. So, let me say that this is minus k times v acting opposite to the motion of the particle, right? And then let me keep the notations as follows. So, my frictional resistance R is equal to minus beta times v. Okay. So, now my equation of motion in this scenario will be as follows. So, we have the total acceleration of the system is the restoring force by the spring plus the restoring force acts always in the negative direction. We have already put a negative here. So, plus the resistance force and plus the external driving of the system. So, this is the external external drive of the system. Okay, and now what we have is in this scenario we see let us start to plug all these situations, all these values. We see that my equation of motion is m dv dt is going to be minus alpha times x minus beta times v, and v I can replace, well, alpha beta times v plus g of t, and then this is going to be m times d2x by dx2, which is minus alpha x minus beta dx dt plus g of t. Okay, so then we can quickly rewrite this equation of motion as follows, that this is also equal to we divide throughout by m. So I see that x double dot plus 2 times k x dot plus omega square x is f of t, where I can map my new variables. So my k is beta divided by m, and my omega square is alpha divided by m, and my f is g divided by m. So force, driving force per unit mass. Okay, so now I'm going to start to work along the lines of this particular equation for the damped and the driven box attached to a spring. Okay, so let us start with some simple scenarios. Undamped springs. So to begin with, we look at the case which is undamped and undriven. So what case is this that I'm trying to see? We see that the case is undamped, which is that the damping term is shut down and the driven term is also shut down, and we are left with a simple equation which is x double dot plus omega square x is equal to 0. And this is a simple case of a simple again the same simple pendulum that we studied in our previous module, and this is or the so called simple harmonic motion, and we can quickly find the solution. There is nothing great about it, and we can also find the period of the system. Okay, so we see that to do that I just want to briefly mention how we arrived at the solution. We assume that my solution is of the form e to the power lambda t, and we plug it into this equation to find that the lambda satisfies the following equation: lambda square plus omega square is 0, and lambda comes out to be plus minus I omega, and we plug our solution to this initially assumed value, and we see that x comes out to be of the form a e to the power lambda I lambda t, well, I omega t, plus b e to the power minus I omega t, or we can write this solution in the form of sine and cos, and that is what we see when we study simple harmonic motion. Okay, so this is of the form c times cos of omega t minus gamma. Okay, so then this quantity c is my amplitude. Let me introduce all this physical term, and omega is my angular velocity, and my gamma is my phase difference. Okay, so then let me also talk about of a case where we have a vertical a body hanging through a vertical spring, right? So what have we got? So a body of mass m is suspended from a spring and can move under gravity, Okay, so in equilibrium, the spring is extended by a distance b. So what have we got here is that we have a body which is hanging by a spring, and due to the mass of the system, right, so the body is going to stretch this spring by, let's say, a distance b. So what happens is at equilibrium or at static, there is the case when there is no motion. At equilibrium we have that the force balance will be mg is equal to k times b, where k is my spring constant. Okay, so from here I can quickly find what is my spring constant. K is mg over b, okay, where b is the length which is stretched due to the weight of the object. Okay, so that is not where we stop. We want to further extend this spring so that the mass can start to oscillate, right? So we expect that the mass is going to, once stretched, will come down, and due to the restoring force, it is going to will have a tendency to go up. That will bring the mass above, and due to inertia, the mass is again inertia and the weight of the system, the mass is again going to fall down, stretching the spring, and again the restoring force will compress, and so on and so forth. So that is the motion we want to see. So so what we have is, the initial condition is the following. At t equal to 0, the body is given a sudden push, is given a sudden push which projects it upwards with speed u. Okay, it is given a sudden push which projects it upward with speed u. Okay, so then we have to find the subsequent motion. Find the subsequent motion of the system. Okay, so then what we have is, let us try to see the example. So let us say we have this spring, of course, and the spring is originally stretched by a distance b, and then when we stretch the spring further by a larger length, so we have b plus, let's say, z, then there will be a restoring force acting on the mass, which is going to push the mass upward, right? So let's say, let z is be my downward displacement beyond the equilibrium, downward displacement, right? And then what we expect is that there will be a restoring, which leads this downward displacement will lead to a restoring force, which is going to be minus alpha times b plus z, right? Because b plus z is the total length of the spring which is stretched. Okay, so then what we have is, if we write the equation of motion, we find that mz double dot is mg minus mg by b times, well, my alpha comes out from my equilibrium equation, that alpha is mg by b. So that is what I am using here, the mg by b times b plus z, and then we can simplify this further. So this is minus mg z. Okay, and then we can solve this again. This equation of motion is z double dot is equal to gz plus gz is 0, and well, are we missing something? Gz by b. And again, this is the same simple harmonic motion where my angular frequency omega is square root G over B, and from here we can find quickly the period to be, the period of oscillation for the system to be 2 pi by omega. Okay. Then let us now start to complicate our situation by introducing damping in this system, in this pendulum case, this spring pendulum case. Okay. So then the next scenario is damped SHM, damped simple harmonic motion. We see that this is going to be x double dot plus 2k x dot plus omega square x, which is 0. We have added this damping term now. That is, the spring exhibits some sort of a damping along with its motion. And then again we choose solutions of the form e to the power lambda t, and lambda this time is going to satisfy the following equation: lambda square plus 2k plus omega square is equal to 0, 2k lambda. And if we solve this equation, we see that lambda comes out, we will have two roots. We can find the two roots. Lambda is plus minus square root k square minus omega square, and then minus of k. Okay, we see that lambda 1 and 2. Okay, so both lambda 1 and 2 are negative, because we see that k square minus, why? Because k square minus omega square magnitude is going to be less than the magnitude of k, because omega is, the angular velocity is a positive quantity. Okay, so from here we find the undamped case. Well, the damped case will have the following roots, and if we solve this, we plug it back into our original assumption, we find that my solution comes out to be the following. So x of t is c e to the power minus kt plus times cos of omega, omega damped times t minus gamma, where omega damped is given by square root k square minus omega square, this following quantity in the solution. Okay, and then we see this time, notice the following change in the solution. The solution is exhibiting some oscillations via this cos term, but also eventually the solution is decaying exponentially. So we expect the solution of this form, it is going to show some oscillations, but eventually it is going to decay exponentially because of this damping term. So this is my damping term, which was not present earlier. And finally, from this oscillatory term, we can find the period. The period comes out to be 2 pi by omega d, and we get the following solution. Notice that even the period comes out to be larger this time, because earlier the period was 2 pi by omega, now the period is 2 pi by square root of absolute value of k square minus omega square, which is a smaller quantity in the denominator. So the final period is larger. So this is larger than 2 pi by omega. Okay, enough of the boring cases. We are now going to look at a specific scenario which is more interesting. That is so-called, where we have the so-called critical damping. That is when the natural frequency of the oscillation of the particle matches with the driven frequency. So let us see what happens in that case. Okay, so what I am trying to say is the following. So we have the so-called critical damping. So this is my case 3 here. Case first was undamped and undriven. Case second was damped and undriven. Case 3 is damped and driven, but driven in a particular, with a particular frequency. Okay, so we have we have, well, before that, I can also look at the roots. We can quickly see what is happening. Even in this damped simple harmonic motion, we can have the overdamped case, the overdamped case. That is when we have cos of, when we have k is greater than omega. That is when both the roots are real, right? And then we can have underdamped case when k is less than omega. That is, we have oscillatory. So this was the underdamped case. Okay, the overdamped case, we will have two roots which are both real, and we won't have this oscillatory term. Okay, and let's see, have we missed any case? No, we haven't. Okay, so then the third case is the critical case, the critical damping case. The critical damping case when k is equal to omega. Remember, the roots in our damping were minus k plus minus square root k square minus omega square, right? So if k is equal to omega, we expect two double roots minus k, and we will have the solution of the form e to the power minus kt plus bt times e to the power minus kt. So notice that both the roots are decaying exponentially, but one of them is increasing algebraically. So if we plot the solution, we will have one of the solution is decaying exponentially, and the other solution is initially rising algebraically for small t and eventually going to decay exponentially for large t. Okay, so that is my critical damped scenario. Let me see how much time. We can briefly also mention the case of the driven system before we wrap up this module. So the driven system, the damped driven system, the damped driven motion. Okay, so what we have is x double dot plus 2k x dot plus omega square x is f of t, right? So we have the damped driven scenario where we have also the motion being driven by the external forcing on the system. So suppose we also assume some form of the driving force. Suppose we assume f of t is the following function f naught cos p of t. So we have a harmonic driving of the system. So let us say that f naught, so we have f is equal to f naught e to the power I pt. So what we are trying to now, so in order to solve this system, let us try to solve this system completely in the complex plane. So we assume complex solution, which means we assume a solution in the complex plane by assuming first that the driving force is f naught e to the power I pt, and then finally we compare the solution, compare the real part of the solution, the real part. Why real part? Because the real part of this complex quantity f naught e to the power I pt is f naught cos of pt, which is what our driving force was. Okay, so we finally find the real part of the solution that we find. Okay, so when we assume a complex solution, so let us say that our x is c times e to the power I pt, the same frequency as the driving frequency. And so by the way, we are trying to find a particular solution. We are finding the particular solution. We are finding the particular solution, and and then so the idea is we find the particular solution, then we add it to the homogeneous solution to get the general solution. Okay, so the particular solution is assumed to be complex, and then we see that my c, C is also complex. After plugging this particular solution in the equation, we find that C comes out to be F naught divided by omega square minus P square plus 2IKP. Okay, and then we have that this is going to be F naught e to the power I. From here we find that X comes out to be F naught e to the power IPT divided by this quantity which is in the denominator. Okay. So that gives us the solution X, and then we take a real part of this solution to arrive at our solution for the final system. So the real part, after I do that, I find my X particular solution comes out to be A cos of P times T plus gamma, where my amplitude A comes out to be the absolute value of the amplitude C, which is going to be F naught square root omega square minus P square whole square plus 4 Kp K square P square. Okay, and we see that my X of t comes out to be, and of course my gamma comes out to be tan inverse of minus 2k p divided by omega square minus P square. That is, if we look at the amplitude that we found, we take the imaginary part and then divide it by the real part, and take the inverse tan, and we get this phase difference. So that completes the discussion for the critical damping case. And then in the next module we will start our discussion with a special case when the critical damping frequency matches with the natural frequency, and what does this particular case leads us to. So thank you so far for listening. Thank you very much.